So thank you very much. Thanks for the introduction. So I will give my presentation today around the topic that basically an innovation when it comes to PFAS degradation. We're trying to look at this topic, which is quite a hot topic now, using two different technologies, membrane distillation followed by electrochemical oxidation. So the outline of my presentation today will include some background and motivation for that study in terms of PFAS persistence in the environment and its associated environmental risks. What are the limitations of the existing limitations of existing technologies currently in use for treating PFAS. I'll follow this up by some objectives in terms of what we did in terms of developing this hybrid process, aiming at degrading PFAS compounds. Then I'll follow that with the methodology, basically covering our experimental setup and experimental conditions and the role of membrane distillation in concentrating the sample to be treated or the waste to be treated, and basically some improvements there. Then I'll follow this up with some of our main key findings, basically the results of the research, and then I'll finish with some future recommendations. So what are PFAS compounds? Of course, most of you know what are PFAS compounds, but just we'll give a quick background information. They are amphiphilic molecules. They have very strong carbon-fluorine bond. Basically, that can be characterized by high bond energy up to 536 kilojoule per mole. And they are resistant to friction and biotic degradation. And also they have high thermal and chemical stability with low vapor pressure. And these compounds can come from a variety of sources that we use on a daily basis. Fast food packaging, paints, photography applications, like non-stick cookware we use all the time in our homes, stain-resistant products, shampoos, firefighting foams, pesticides, and so on. So for PFAS exposure, we always get exposed to PFAS as humans and also as living, in the environment as fish and other wild animals if they get exposed to water containing PFAS. But as humans, we get exposed through water contamination, air, indoor pollution, soil and vegetation, exposure to them basically through exposure to soil in the environment or when we consume foods that have PFAS in them and other consumer products and so on. So these PFAS compounds, they have a lot of toxic effects and can be characterized by causing kidney disorders, higher cholesterol, storage in our organs, can cause some immune toxicity, changes in our bodies, and also changes in liver enzymes production. So what are the different methods currently in use for treating PFAS compounds containing wastewaters? It could be physical treatment such as adsorption processes, some physical chemical separation such as sedimentation if PFAS compounds are attached to solids, so they can be separated by settling processes. You could have also membrane filtration. So all these are characterized to be physical. Chemical processes to remove PFAS compounds can be advanced oxidation or degradation processes, some coagulation and precipitation. These are the So chemical processes, these could be processes like coagulation, flocculation, precipitation. These are the processes for sedimentation or settling, or it could be advanced oxidation or degradation processes. You could also look at biological treatment, but the problem with biological treatment that they are very slow processes, especially with these compounds, because they are hardly degradable or biodegradable. And these processes could be aerobic, anaerobic, and could be designed in different ways, including membrane bioreactors, but their success is quite limited because of the slow process. So you could have also within the membrane category as membrane filtration, You could have actually membrane processes, and in these processes, you could have actually different driving forces. One of them could be hydraulic pressure if you're looking at ultrafiltration, micro, nano, and RO, or could be temperature driven, like as a driving force for the membrane filtration, could be concentration driven, so for forward osmosis, or electrical voltage, like these ones used for electrodialysis. Okay. And the focus of my presentation today will be coupling these advanced oxidation or degradation processes along with the membrane concentration. So for the membrane distillation, as a membrane process here, the driving force is basically the difference in the vapor pressure between the two sides of the membrane. And the advantages are low working temperatures, only up to 80 degrees Celsius, can use waste heat and renewable energy as a driving force, and the simplicity of the system. And in this system here, you can see from the schematic here, you have actually the hot feed stream here, and this hot feed stream on one side of the membrane, on the other side will be the clean permeate stream, and the driving force is the temperature gradient between the two sides. And based on this temperature gradient, then you have actually the permeate flux progressing through the membrane from the side of the concentrate to the side of the permeate. So this is the working principle of these membrane distillation processes. And for the electrofenton, as basically the process we included here as advanced oxidation happening between the two electrodes in this electro-oxidation process. So in this process here, you have actually reactions taking place at the anode and reactions taking place at the cathode. And the bottom line in this system here that we want to generate actually from these reactions, these highly reactive species or radicals. These are the hydroxyl radical species. Once they are formed in the water, they can react very quickly with the pollutants, and they can actually lead to the formation of water and CO2, which means we have generated a system that's reaching mineralization. Okay, so in this system here, the key components are the ferrous ions and hydrogen peroxide being generated that can react with the ferrous ion, okay, to form the hydroxyl radical. And we can also, in this reaction, we can form the ferric ion that can be actually can go through the reduction process or reaction to reform again the ferrous ion, so we can keep regenerating these ferrous ions in the system. So how to remove PFAS compounds? So we start with the membrane process for concentrating the stream. So the advantage of this system is that we can remove actually PFAS compounds if we can do that directly on its own only. So we can have actual high rejection stream, but the problem is that we can generate high concentration waste stream. So then we end up with more waste. So you have to deal with the waste again, right? So if we look at another process, electrochemical advanced oxidation processes. So the advantage of these processes that we can have high efficiency to degrade and mineralize the persistent pollutants, or at least degrade them into compounds that are easily attacked or easily treated by a subsequent process. But the disadvantage of this system or electro-oxidation processes that the slow degradation kinetics involved and high energy consumption. So if we can combine the both processes like AOP and membrane separation, maybe as a hyper process, of course, we can treat the retained compounds in the concentrate stream of the membrane process before disposal, increase the concentration of the pollutants in that waste stream to be treated. And this way we can minimize the energy use per gram or per kilogram of pollutant degraded. And we can actually achieve faster electrochemical degradation kinetics and less energy consumption per molecule or per kilogram of molecule to be degraded. About this hybrid process, this is a hybrid process that was actually generated by the team. And this team actually consisted of a PhD student, Ms. Afrouz. She's a PhD student working on this project under the supervision of Dr. Mohamed and myself from the University of Alberta. So this is actually a project that's involving both mechanical engineers and civil or environmental engineers. And in this system here, we start actually with the membrane system okay? That actually, this membrane system, basically hydrophobic membranes, that actually receive the water from the feed tank, and by doing that, then we can actually concentrate the sample into this permeate tank, and this permeate tank as a concentrated sample or waste stream, including PFAS. This is a system that to be treated by the electrochemical oxidation, okay? So regarding some characteristics of the hydrophobic membrane, as you can see from these SEM images, and this is what it looks like actually, and this is the structure of the membranes, and it's quite homogeneous actually structure, and with the voids being actually homogeneously distributed in the system or in the membrane unit. And regarding actually the water contact angle, as you can see, the water contact angle is about 121 degrees Celsius. So that clearly indicate that this membrane was clearly successful in the synthesis to be hydrophobic. Regarding the electrode material, in this system here, we used actually two different electrodes, one active and one non-active. So the active one, it could actually be platinum, carbon, or mixed metal. That involves actually or characterized by low oxygen evolution over potential, and hydroxyl radical generated or OH dot are actually chemosorbed at the anodic surface. Regarding the non-active one, it could be a variety of options, but the best one is the boron diamond or boron doped diamond electrode, BDD, and it actually can generate a lot of actually oxygen being evoluted or generated in the system, and the hydroxyl radical generated is actually generated at a high rate actually and content, and actually this gives a large potential window for actually them to be these radicals to be resorped at the anodic surface, and that will allow for a lot of reaction to take place and fast degradation or faster degradation at the anodic surface actually of these PFAS compounds, okay? And in this system here, the fentanyl reaction that takes place is, as you can see here on the screen on the left side here, and this fentanyl reaction is the reaction that from which we generate the hydroxyl radical, and at the anodic surface here, the hydroxyl radical actually can also be generated, and this actually generated hydroxyl radical absorbed at the surface of the anode can leave actually or can lead to the degradation of actually the compounds at the surface of the anode in that system, electrochemical unit actually or cell. Okay. And by doing that, then actually the degraded compounds, are actually less or shorter chain compounds and could be actually dealt with in a subsequent process, or if this process can be continued and for a longer time or with more circulations, then these compounds could be degraded completely through CO2 and water. So regarding the control experiments, we use the control experiments here to investigate the influence of electrooxidation at the anode, and to investigate the air bubbling effect and the absorption capacity of the electrode materials on the PFOA degradation. As you can see from these experiments here on the left side, the TOC removal actually increased quite a bit, actually, and as TOC increased, the PFOA removal also increased. And we did the PFOA measurement directly, but also we used the TOC or DOC basically as a surrogate indicator. And regarding the removal efficiency ratio, as you can see here, with air bubbling, and on the right side graph with the air bubbling, actually, we had actually higher removal efficiency compared to without air bubbling, which means air bubbling improved the removal. And regarding the effect of the current density on the hydrogen peroxide production in the system, as you can see from the left-hand side here, the hydrogen peroxide concentration being generated in the system increase with increasing the time of the treatment, and also increase with increasing actually the voltage, or the current density, sorry, which is characterized by the amperage per surface area. So as it increased from 50 all the way to 500, we increase the production of the hydrogen peroxide. Of course, the sweet point would be somewhere in between to minimize the power consumption in the system. And on the right side, you can see the effect of the time of treatment on the H2O2 generated in the system, again, with actually BDD or combined BDD with MD as a material for the anode here, and at the same power or the same actually current density, 150 amperes per square centimeters, as you can see here. With that combination, BDD with MD, actually with the membrane distillation with BBD, we increased actually the degradation or of course, the hydrogen peroxide generating system, and thus the degradation later on, as we'll show you in the system. So that actually combination of the BDD with membrane distillation worked better than the BDD alone actually, or degradation alone in the electrochemical cell. And regarding the influence of the applied current density on the performance of the system, again, on the left side here, you can see actually the degradation ratio here, kind of efficiency, but as a ratio or as a fraction. And it actually reached a maximum capacity after 6 hours, but actually started to reach a plateau only after 1 hour, again, with increasing the amperage from 50 to 500 increased quite a bit. And as you can see here, fast degradation and then slowing degradation. So 2 zones of degradation, as you can see here, from 0 to 1 hour, and then following the first 1 hour, the degradation slows down and then actually starts to plateau quite a bit till we reach the maximum around, somewhere between 3 to 6 hours, okay, depending on the density, current density. And the same thing here, as you can see, with the TOC, almost no degradation with the 50, and the reason for that is that probably after using this 50 amperage per square meters, the PFAS compounds are not actually degraded to quite short change. That's why we don't see much change in the TOC results, but we can see definitely change in the TOC results at higher density, which means the degradation is taking place to shorter chains, actually, compounds. And regarding the influence of the thermal dewatering on PFOA mineralization and degradation, as you can see here, that the TOC, again, efficiency on the top left side here, and this was done at 50 amperage per square centimeters. Again, BDD alone didn't show any change, but when we combined the BDD with membrane distillation, huge improvement. And when we looked at
Dr. Mohamed,
150,
you have
yes?
5 minutes. 5 minutes.
Okay, I'll finish up quickly. So as you can see from those results, increasing the membrane density or current, actually, or the density current here, improved the degradation quite a bit, going from 50 to all the way to 500. Okay, and the table here shows the apparent rate constant, and again, the apparent rate constant increased actually quite a bit at the 500 compared to at BDD 50. So some actual improvement was observed quite a bit. And regarding actually the contribution of EF and BDD oxidation mineralization PFOA, so this one here shows the contribution of the BDD alone, EF compared to absorption alone. So as a basically as kind of like a control. So the majority here is happening due to the oxidation and not just the absorption alone, right? And regarding some identified generated organic intermediates, we did the high resolution mass spec analysis, and we generated a lot of different intermediates with shorter chain compounds, and this was the intention of the treatment. And regarding the products of the degradation, we characterized them and we identified them using that high resolution mass spec system. And as you can see, with the time of treatment, the fluorine concentration increased, which means we defluorinated the compounds quite a bit. And that means we also removed basically the TOC, but along the way, we also formed the short chain compounds. Regarding the mechanism of the PFOA mineralization, this is a mechanism here as identified by our study. And that study was actually published, and feel free to send me a note and I'll share the paper we published with you. And this is the mechanism of the degrading the compounds leading to their mineralization. Again, these are the specific reactions highlighted here. As you can see, those reactions leading to the degradation of the compounds or the parent PFA compounds, or PFAS compounds, sorry, and the chain shortening leading to the new short chain, basically compound being generated. And regarding the specific energy consumption and calculated by this equation here, as you can see here, for different times, 2, 4, and 6 hours, the energy consumption was characterized actually, or the specific energy consumption was characterized for these different processes. BDD was membrane distillation compared with only BDD. And as you can see here, things actually quite improved again with BDD and ND combination. So regarding the conclusions, increasing the current density led to having higher concentration of hydrogen peroxide being generated in the system. And also increasing the current density led to enhancing the degradation and mineralization efficiency. And dewatering the feed solution leads to an increase in the feed concentration of the PFAS compounds and this led to the enhancement of the electrolyte conductivity. So the performance of the MDEF improved significantly compared to the EF process alone, especially at the current density of 50 amperes per square meter. And then we identified all the main generated organic intermediates during the process of the degradation, and we found out that the possible pathway of PFOA degradation was through the reactions I showed you. And we also decreased the specific energy consumption by dewatering the feed solution to have a higher concentrated waste stream. These are the future recommendations. We are aiming at scaling up these field demonstrations or these lab scale demonstrations through some field piloting and to treat actual wastewater containing actual PFAS concentrated streams. And also regarding the BDD electrode replacement and sustainability, we are going to look into exploring some other electrode materials that could be a lot cheaper and also could be more actually sustainable, yet can have still the similar performance like BDD or close enough. And we're going to be also doing some toxicity monitoring by working with the people from biological sciences to look at the real waste stream and the treated waste stream toxicity impacts. And finally, of course, if we're scaling up and trying to commercialize this, we're going to look at actually LCA analysis along with other techno-economic assessment. And finally, testing with some real potential wastewater at some facilities. I'd like to actually thank all the contributors to this study. For my collaborators, Dr. Mohamed, Sararzada, and myself, we get the variety of funding from different sources, from the federal government, NSERC, and local actually sources as well, and all the way to actually funding that received from Future Energy System at the University of Alberta, among others. Thank you very much. I'm sorry for taking a bit longer time. Thank you.